Welcome. In this section we talk about antiderivatives. We've made it to 4.9. That's the last section in chapter 4 that we'll cover. While differentiation is a process that you know, antidifferentiation is basically the same idea but in reverse. A function f, and we denote it with a big F, a function big F is an antiderivative of little f if big F prime of x equals little f, if the derivative of big F is little f. For example, 2/7 x to the 7 is an antiderivative of 2x to the 6, and we check this by taking the derivative of 2/7 x to the 7. Yep, we get 2x to the 6. 1/2 x squared plus 146.7 is an antiderivative of x, and you check it by just taking that derivative. Here's a fact. If f is an antiderivative of little f, then all antiderivatives of little f have the form big F of x plus c, where c is a constant. So, for example, let's look at these antiderivatives of x. This 1/2 x squared plus 146.7 is a little complicated, right? Because it has that 146.7. But I could also say that 1/2 x squared is an antiderivative, I'll just write AD, antiderivative of x. And 1/2 x squared minus 13 is an antiderivative of x. One thing you notice is when I take derivatives, every function has just one derivative, but with antiderivatives there can be several antiderivatives. Right now I've seen 3 different antiderivatives of x. They don't look all that different though. 1/2 x squared plus 146.7, 1/2 x squared, 1/2 x squared minus 13. Do all antiderivatives of x look like basically 1/2 x squared plus a number? Yes, that's exactly what this fact is telling me. There's nothing stranger than that I could possibly get. What do all the antiderivatives of 2x to the 6 look like? Well, here's one of them, 2/7 x to the 7. So all antiderivatives look like 2/7 x to the 7 plus a constant. We typically use a capital C to represent the constant there, and this expression just means a family of functions, all possible functions of the form 2/7 x to the 7 plus some number. Okay, a little practice. I'll do these and see if you can predict before I do them what the answer is. An antiderivative of cosine x. How about sine of x plus 8? I just need to find one of them. I'm asking for an antiderivative. 12x to the 11. How about x to the 12 minus 3? Why not? This one's a little more challenging. 1 over x. What is an antiderivative for that? Do you remember natural log? Natural log of x? So this is a good start. In fact, that's actually a lie. I'll tell you the real answer is the natural log of the absolute value of x. And here's why. Let me draw my 1 over x function. There's 1 over x, 1 over x, and next I'll draw the natural log function. Here's the natural log, so ln of x. And you can probably justify by looking at slopes that the derivative of a natural log is 1 over x. Initially these slopes are very big slopes, so I have very big values, and then my slopes become less and less but still positive, and 1 over x the values become less and less but still positive. But 1 over x has a negative part also, and so to find a function that's the antiderivative of that, it turns out all I have to do is take my natural log and reflect it over the y-axis, and that's the natural log of negative x. Well, I can combine both of the natural log parts together by simply writing the natural log of the absolute value of x. Alright, continuing on. How about an antiderivative for e to the x? E to the x, excellent. Antiderivative for 9, 9x plus any number you want. Okay. And how about 3 over x? 3 times the natural log of the absolute value of x. How about a few more? Pause the video now, give these things a try, and then restart when you're ready to check your work. Okay, let's see, an antiderivative. So x to the 9 is a good choice, but if I took a derivative of x to the 9, I'd get a 9 out front. So I'm going to put 1/9 out front, so that when I take the derivative, that 9 comes in front, it multiplies with the 9th, gives me 1, and I'm left with x to the 8. Well, this one is pretty similar. It only has a 4 out front. So what if I write 4/9 x to the 9? Can you confirm by taking the derivative that that works? 1/2. Well, 1/2. What if I just wrote that 1/2 out and then took my antiderivative of x to the 8, which is 1/9 x to the 9. Does that work? Yeah, that should work, because this is just, let's see, 1/18 x to the 9. When my 9 comes out front, it multiplies with the fraction to give me 1/2, and I'm left with an 8. All right. By a similar reasoning, x to the 3/4, I want an exponent that's 1 bigger. How about 7/4? Well, what should come out in front? The reciprocal of that, 4/7. When the 7/4 comes out front, it multiplies with its reciprocal and just gives me 1. I subtract 1 from the exponent, and that leaves me with 3/4. Square root of x, a little more challenging. Let's rewrite this. Square root of x is really x to the 1/2. So for an antiderivative, I'll raise that exponent by 1 and multiply in front by the reciprocal. X to the n. Anytime I have x to a power, in general, what does the antiderivative look like? I'm going to do lift that exponent by 1, x to the n plus 1, and multiply in front by the reciprocal of that new exponent. And you can confirm by taking the derivative that n plus 1 will come out front, give me a 1, and I'm left with x to the n. All right, moving on. Indefinite integrals. So far we've talked about an antiderivative. Now we have a way to represent all antiderivatives. It's the curvy S thing. So curvy S x dx means all the antiderivatives of x, which we know is 1/2 x squared plus c. So this expression is called the indefinite integral of f. It shows us the whole family of antiderivatives. The indefinite integral of x to the 8 is 1/9 x to the 9 plus c. How about some other indefinite integrals? The indefinite integral of x to the 4, 1/5 x to the 5 plus c. The indefinite integral of secant squared. Oh, I need an antiderivative for secant squared. I think tangent is an antiderivative, so tan x plus c. All right, let me rewrite the problem on this one. X to the 1/5 dx. So the indefinite integral of this will be, let's see, lift the exponent by 1, so x to the 6/5, multiply in front by the reciprocal, 5/6, add a c, and you're good. Last problem. Do you know what the answer is? How about 8x plus c? We have a couple nice rules that will help us simplify problems. The first is the constant multiple rule. The antiderivative of k times f of x is the same thing as k times the antiderivative of f of x. So for example, the indefinite integral of 3 secant squared x dx is really equal to 3 times the indefinite integral of secant squared x dx. And so that's just 3 times tan x plus c. And we have one more rule that's very useful, the sum rule. If I have an indefinite integral of a sum, I can add the two indefinite integrals separately. Let's see, for example, the indefinite integral of x to the 4th plus x to the 8 dx is really the same thing as the indefinite integral of x to the 4 dx plus the indefinite integral of x to the 8 dx, which then is just 1/5 x to the 5 plus 1/9 x to the 9 plus a constant. All right, last big idea in this section, differential equations and initial value problems. A differential equation is an equation that involves the derivative f prime of x. So here is a very simple example of a differential equation. F prime of x equals x to the 4 minus 3x. The goal in differential equations is to figure out what is the original f that took place in there. So a related problem is called an initial value problem. Not only do we have a differential equation, but also we have an initial value. So we have a differential equation and the value of my function f at some particular point. Let's see how this works. How would we solve this initial value problem? So the first thing I do is solve the differential equation. Here I can simply anti-differentiate. If f prime of x is x squared minus 10x, then f of x looks like 1/3 x cubed minus 5x squared plus some constant. And I don't know exactly what that constant is, but here's where the initial value is really useful. Because f of 1 is 1/3, I can just plug in a 1 into my x. Okay, well that's my f of 1. I've just simplified f of 1, but I also know that f of 1 is 1/3, so 1/3 equals negative 14/3 plus c. And now, solving for c, this implies c equals, let's see, 15/3. Oh, it's just 5. c equals 5. So it's this initial value that lets me figure out the exact value of c that I should use. So now I have a solution to the initial value problem, and that is f of x equals 1/3 x cubed minus 5x squared plus 5. And that is the solution. All right, those are the big ideas in 4.9 antiderivatives. Give the problems a try, do the worksheet, and of course, let me know if you have problems. Thanks.